whenever it's necessary. Right? When we have derived part of them on the board, the rest of them are available in the appendices, and I expect you to at least derive a few of them on your own. Right? Any questions? Then we will move on to, before we move on to discussing specific problems, right? We look at the cylindrical and spherical polar coordinate and give a geometric view of the cylindrical and spherical polar coordinate, so that you're clear what are the coordinate lines and what are the coordinate surfaces that these will figure prominently in the solution of problems. It will give you a clear idea. For example, if you want to calculate a force on a surface of a sphere or a cylinder, it is important to know how to calculate the force or flow through, it is flowing, for instance, through a cylinder, or it will be flowing also from the surface of the cylinder, which might be permeable. So we need to know how to handle, all these situations, right? So for that, let's take a closer look at the cylindrical and spherical coordinates. I'll call this as 1, 2. This may also be regarded as x and y, sometimes in the rectilinear coordinate system. So let's look at the cylindrical. Right? We look at identify what are the coordinate lines, and more importantly for our calculations, what are the coordinate surfaces. Right? So now for the cylindrical coordinate, this would be x1, x2, x3, any point. We have already defined this. This is the angle made by this projection onto the xy plane. This is phi. Right? In the cylindrical coordinate, I can take it as being measured from the x-axis of the O1 axis. This is RC, and this is ZC is equal to Z. So analytically, it can be written as x1 is equal to RC cos phi, x2 equal to RC sin phi, and x3 equal to ZC. Inversely, I can write this as RC is equal to x1 squared plus x2 squared power half, or you can write it as x squared plus y squared power half. Right? And phi is equal to tan inverse of x2 by x1, right? And ZC is equal to x3. Right? So that's what I have. So what is the RC line? Because we have identified the x1 line, x2 line, and x3 line are along the three axes. So what are the axes for the cylindrical coordinate? Right? So we have seen that the RC line is nothing but this line extending. Right? Because by definition, the RC line is for phi and ZC being constant. Right? The RC line is the line along which the RC varies. So phi is a constant, right? And ZC is also a constant. So phi is a constant. Now I'll call ZC to the 0 for convenience. It can be any constant, right? If I make it ZC to be equal to 0, that corresponds to the xy plane. If phi is constant, the RC line is given by this. Right? So you can also easily verify analytically if phi is a constant, then x2 by x1 is a constant. Right? And x3, if ZC is a constant, x3 is also a constant. Right? So if I now make this 0, it's nothing but x2 by x1 is a constant. What equation does it represent? The equation of the straight line on the x1, x2 plane passing through the origin, which is exactly what it is. even though it's a curvilinear coordinate, the RC line is a linear coordinate. That's what we find, right? Phi, of course, the phi line is this line, right? And again, the phi line is actually the equation of it will turn out to be the equation of a circle, right? The phi line is given by RC equal to constant and ZC equal to constant. Again, for convenience, if I take this constant to be 0, then I am looking at the xy plane or the x1, x2 plane, right? So RC equal to constant is x1 squared plus x2 squared over half is a constant, right? Ankit Kumar, where is your attention? See, nobody forced you to register for this course. I can let your total disregard for any basic decency and courtesy go unnoticed, but it would send a wrong message to everyone else that I am actually allowing it. Right? So you can still drop out of the course. That's what I would advise. So I have x1 squared plus x2 squared is a constant, which is half is a constant. x1 squared, that's the equation of a circle. So that is the phi line. Right? It's a circle on the xy plane, but that's because I've chosen ZC to be 0. It's all circles parallel to the one that I have drawn. That's the curve along which the phi varies. Right? So the ZC line is nothing but the x3 axis. That's the same, again a line. The only curvilinear coordinate is really the phi coordinate. So it traces a circle, certainly not a linear curve. Right? Now if you look at the constant surfaces, the constant RC and the constant, coordinate surfaces, right? So we look at three surfaces, and you will see that because we have already verified that this is an orthogonal system, right? And that the tangent lines, the vector tangents to the coordinate lines are actually proportional. In two of the cases they are equal to the normal to the coordinate surfaces. You can expect the coordinate surfaces would actually be normal to the coordinate lines, right? So, or rather the opposite, the coordinate lines would be normal to the coordinate surfaces. Let's now look at what would be the constant surfaces. Let's take first the RC equal to constant surface. Because that's how we have the line between two constant equations. Two of the coordinates would be constant. The coordinate surfaces are given, identified by which coordinate is a constant around that surface. That defines a surface in the three-dimensional space. So clearly, the RC equal to constant surface is x1 squared plus x2 squared over half equal to a constant. Right? This of course looks like the equation of a circle, which it is in the x1, x2 plane, but z is left unspecified. It's valid for all values of z. Right? So what it means is that it's actually a cylinder of radius given by RC, whatever RC you might choose. That is the equation of the surface of the cylinder in three-dimensional space is given by this x1 squared plus x2 squared equal to a constant. Right? Whatever you might specify. So if I fix the RC, right? And so I draw a circle. This is the equation of the circle, the x1, x2, but we are looking at this equation in three-dimensional space. So this would be valid on all points of a cylinder of radius RC, and extending whatever length you want. Right? So this is the actually a cylinder of radius the surface. This is only this. You have to distinguish between the. Here I am identifying a particular line. Here I am phi equal to constant RC line is the line that I have identified lies on the x1 x2 plane. For convenience I have chosen this. So other RC lines would be parallel to these lines because phi is fixed, right? So that would be parallel on top of each other. So another line I am not good at drawing these. So you have to consider lines, or you consider this plane which makes an angle phi. So all lines on this drawn like this, they are also constant RC lines for different values of ZC. I just found it convenient to draw the one for which ZC equals 0. That is not to be confused with this, right? This is the surface. So you have to understand what the equation of a cylinder is. Cylinder is the surface of the cylinder. It is actually represented by this. Right? So this represents a cylinder, right? And so if you look at this, we finally normalized all the unit vectors and got one set of vectors. So the tangent to the coordinate lines, right? The tangent to the RC line and the normal to the RC to the constant surface is what you have to now identify as ERC. Clearly, that is what it is. Go back to it. Normal to the constant RC surface. That's also ERC. This will become very important. This is particularly important. The normal, looking at this as a normal to the coordinate surface. Because as I already pointed out, two examples. One, for instance, involving the mass flow rate passed across the area, that would involve OV dot NdA, okay? Or the contact force, which would again involve an integral over the area. So it's important to know over what surfaces you integrate, right? Typically, the cylindrical, once you've chosen the coordinates, this is all in the Cartesian space, three-dimensional space, right? Often we would require only calculations across the coordinate surface. So the calculations can do, now going to outline how to do those calculations properly, right? And rigorously, without any confusion, right? So that is it's a prelude to this. So it's important to understand how the tangent lines and the coordinate surfaces and the tangents and to the coordinate lines and the normal to the coordinate surfaces are related, right? In this case, finally, it would form a normal to the constant RC surface, which is the surface of the cylinder, right? Let's now look at what about the phi equal to constant, right? Again, this is the surface in the three-dimensional space, right? So that is tan inverse x2 by x1 equal to a constant. So I can call this as x2 is equal to m times x1, or y equal to mx. Clearly, this is an equation of a line in the two-dimensional x1, x2 plane. But in the three-dimensional, this would be nothing but an equation of the plane which has an angle phi, the plane that I have just highlighted here. That is the equation. Along the plane, you can see that x1 and x2 will have this. Because z is varying. Z can be anything, but all points on the plane will satisfy this equation. Right? Because this is fixed. So this is the constant phi surface. And this will, so again, the tangent, the normal to the phi equal to constant surface is equal to the tangent to the phi line, and that is what is given by E phi. Right? So we know that is this actually, it's the tangent to this E phi at any point. So now the other one, very easy to write down, x3 equal to, or rather what we want is zc equal to constant. Is equal to x3, this is nothing but the x1, x2 plane. Right? x1, x2 plane, the x3 line has the E3 and EZC AC are the same. The tangent line here is the z-axis. That is the line, the normal to the surface, the coordinate surface is the x1, x2 plane. That's also EZC. So this we would have to match with this. Tangent to this line and the normal to this surface are the same. They are proportional in general, right? If you calculate them, one of them was proportional, the other two were actually identical in the way you calculate it, but it only indicates a direction. Our idea is finally to get a unit vector in each of the three directions. So this gives a geometric picture of the cylindrical coordinate system, right? So now when you have an orthogonal coordinate system, right, if for instance a curvilinear coordinate system, you can identify what are known as metric coefficients